Hello, my students. I'm making this video to help you with lab number 10. In this lab, you are going to design an RC oscillator using 555 timer IC or chip. Okay. First of all, I want to make a definition. What do you mean by oscillator? Okay. So let me make it clear here. So an oscillator, it's a circuit. So here we have a circuit here. We call this circuit is an oscillator. Okay. This circuit does not have input, so there is no input, but it has a DC bias. For example, it can be VCC, ground, whatever. So it has DC supply, and this signal should generate here an AC signal. This AC signal can be sinusoidal, it can be triangle, or it can be square wave, whatever it is. So that's what we call oscillator. So we have any circuit that doesn't have input and actually is generating a periodic signal like this one, so we call it an oscillator. So in this lab, you will learn how can you use 555 chip in addition to RC, resistor and capacitor to create a square wave signal like this one. Okay. So let me go to. Yeah. So first of all, that's what I'm saying here. In your lab kit, you have a chip. This chip is 555, as you see here. This chip has how many pins? So it has 8 pins, 4 here and 4 here. Okay. It has 8 pins. Sorry. Yeah. So you see here, let's see what, as you know, I don't need to repeat it, similar to 471. So here, similar to 471. Okay. Here you start counting from here, and then you can go clockwise. I think this counterclockwise, as you see here. Okay. So the first pin here with ground, so you have to connect ground here. This pin, we call it VCC, pin number 8. And as you will see, this VCC is actually between 5 volt and 15 volt. And this is actually the DC supply. So here we need to give the chip DC supply. This DC supply, as you see here, pin number 1 is connected to ground. Pin number 8 should be a positive voltage, 5 volt to 15 volt. Okay. So that means you need to have a battery this way, connected this way, and the ground is here. Okay. And then we have other inputs here. In this lab, we're not going to use all of them. Okay. For example, if this is the output, you will get the output from here. That means the square wave is generated from pin number 3. We are going to use here, we have threshold, we have discharge, we have trigger. These are the 3 pins we are going to use. For the other 2 pins, they are not used in this experiment, but they can be used if you want to do something else, because this 555, it has other applications than oscillator. Okay. So let me go through what I wrote here. So here, I'm going to use this chip in a stable mode. So the word stable, that means it is not stable, which means oscillation. Okay, so there is no stability, high, low, high, low, high, low, and so on. Okay. So the data sheet for the chip, you can find it here. Now, let's see how the chip looks like from inside, and how this chip is going to, at the output here, is going to generate a square wave. Let's see. So as you see here, this chip first, internally, it has 3 resistors this way. They are equal resistor, 5K each, and they are connected this way. Okay, they are connected between pin number 8 and pin number 1. As I told you, I'm gonna connect pin number 1 to ground, and then I'm gonna connect pin number 8 to VCC. And because they are equal, so the voltage drop across them is the same. Okay, so it's gonna be divided equally. That is why the voltage drop here is actually VCC divided by 3. The voltage drop here is VCC divided by 3. The voltage drop here is actually VCC divided by 3. That's why the voltage here is 1/3 VCC. Here, 2/3 VCC, because we have 1/3 here, another 1/3 here. Finally, you add one more thing to get VCC. Okay, so the way it is made here is whatever voltage you put here. For example, if I put here, for example, 15 volt divided by 3, that means this one here, 30 VCC, which is 5 volt, and this one should be 10 volt. If you decide to make this one 9 volt, so actually this one should be 3 volt, and this one should be 6 volt. This is internally, as you see. This is the first part. This is the first part of the chip. It is, it's a voltage divider made out of 3 equal capacitors. This is the first part. Let's look at the second part. In the second part here, we have 2 comparators. So I already explained in this course what comparator is doing. So here you see we have 2 comparators. So what happens here, every comparator, this is a positive input, negative input, okay? If the voltage here, V plus, is greater than V negative, so the output here is going to be high voltage, which is equivalent to logic 1 in digital systems, okay? If the negative is greater than positive, this is going to be low voltage, which is equivalent to logic 0. So you can see here, guys, the output of these 2 comparators is either 0 or 1. And then we have here a latch, okay? Let's see what is the input here. So one input here, guys, at the negative is 2/3 VCC. The other input here is connected to pin number 6, which we call it a threshold. Okay, make it easy. I will make it easy. So the voltage here at pin number 6, if it is less than 2, if the pin number 6, it is less than 2/3 VCC. Okay, so the output here should be 1. Very easy, right? However, if it is greater than 2/3, if this pin positive here greater than the negative, which is 2/3, the output here is 1. But if it is smaller than 2/3, okay, that means the negative is greater than output here is 0 volt. Okay, same thing for the other one here, but for the other comparator, it's gonna compare to 1/3. So one comparator here is this one. I'm gonna call it threshold comparator. This one I'm gonna call it trigger comparator. Okay. So this one, the first one, the threshold comparator is going to compare pin number 6 to 2/3 of VCC. But the second comparator with trigger comparator is actually comparing pin number 2 to 1/3 of VCC. How it works is very simple. If the voltage of pin number 2 greater than 1/3 VCC, if this voltage is greater than, that means negative is greater than positive, the output here is logic 0. But if it is less, so if pin number 2 here is less than 1/3, okay, that means the positive here is greater than negative, the output here is logic 1. High voltage, which corresponds to logic 1, okay? So as you will see, I'm gonna connect here, so we are gonna connect some circuits here in 2 and 6, so that this voltage will change. But anyway, now we have a latch, as you see here. For maybe some of you don't know what is latch, but I will try to explain it. For the student who took 2140, they know what is latch. So here in this latch, this is how it works. Look here, guys. When we have to input R and S. If R is 1, S is 0, so this latch is gonna make a reset. Reset means Q is 0, and this is Q prime. So always is gonna become 1. Okay, guys, if you are confused between logic 0 and logic 1, so actually, high voltage and small voltage. That's it, okay? And this is the first case. And you can see here Q prime is connected to a transistor here, as you see. This transistor is acting like a switch. When the input is logic 1, which means high voltage, you actually turn the transistor on, so it becomes a short circuit, okay? Because it's like a switch, okay? This is in this case. In another case, if we have 1 here and we have 0 here, so this is the case of a set. You are making a set. That means Q here is 1 and Q prime is 0. Okay, and because this is a 0, the transistor is open circuit. Okay, so the transistor is a short circuit or open circuit. Okay, the third case you need to know is we need only 3 cases. when it is 0, 0. So 0, 0 means no change. What do you mean by no change? That means if the output is 1, it's going to stay 1. If it is 0, it's going to stay 0. No change. Okay? So this is the 3 cases we need here. The last thing here, we have like a voltage follower here, something like a voltage follower, and also we have inverter. What do you mean by inverter? That means when the output here is 1, output here has to be 0. If it is logic 0, output here should be 1. Okay, so you invert Q prime. Okay, by the way, here 1 should be VCC. That's why the output here should be either VCC or 0. If it is 1, VCC. If it is logic 0, that means should be 0 volt. Okay. So now I explain how the 555 looks like from inside. What I'm going to explain right now, how we are going to connect. You will see it is just a very simple circuit. How we are going to connect external resistors and capacitor to generate a square wave, as you see here. So all what we have to do, guys, number 1, very simple. You have to connect R1 between pin number 7 and between pin number 8, which is VCC, okay? Number 2, you have to connect another resistance, we call it R2, between 7 and 6. And you have to short pin number 6 and 7 together, and now you have to put a capacitor here. Is that okay? And usually I think in this one, you will need, most likely, I'm not saying it is a must, but most likely you are gonna use electrolytic capacitors. So polarity is very important, as I told you in the lecture. If you switch the polarity, it may explode. Okay, so you have to be careful here. That means positive has to come here and negative has to be here. Okay, if you use electrolytic capacitor. If you use a ceramic capacitor, it doesn't matter. Polarity doesn't matter. Okay, but most likely it's going to be because most likely you need high value for C. Okay, and if you can do it using ceramic, I'm okay, but most likely in ceramic the capacitance is very small. But anyway, and the output, you are going to get the output from number 3 here, which is actually 0 VCC, 0 VCC. Is that okay? We are generating a square wave. Now, and this is the interesting part. Tell me how this circuit, so you are telling us this circuit here, this is a 555. That means if you just connect this resistance capacitor, and I make a short circuit between pin 2 and pin 6, and then this is what I'm going to see in the output. Okay, can you explain to me why this can happen? What's the role of the comparator? What's the role of transistor, and so on? That's what I'm going to explain right now. Okay, very easy. It's not difficult. Very interesting. So look here, guys, how it works. So you see here in the very beginning, the capacitor is empty. There is no charge. So the voltage here is actually 0 volt in the very beginning. Okay, because this is 0 volt and this is 1/3 and this is 0 volt and this is 2/3. So that means here I'm going to have 1 here because positive is greater than negative. We're going to have 0 here, okay, because negative is greater than positive. And as I told you, this is the set case. That means this is 1, that means this is 0, that means the transistor is open circuit, that means the output here is 1. That's why you can see initially the output here is 1. Initially, this is the capacitor voltage is 0. Initially, we're still in the very beginning. And then what's going to happen is that current is going to flow from here through R1 and R2. It's important. So during the charging, current is going to flow through R1 and R2. And because of that, because of the current is flowing, capacitor voltage is going to increase. Okay? For sure, if I leave it to charge, it has to go all the way until VCC. But that's not going to happen. You will see why. So if I leave it to charge, the steady state should be VCC. But it's not going to happen. I'm going to tell you why. The first milestone here, when it goes to 1/3 VCC, will this make any change in the circuit? Let's see. So here, when the input here is 1/3 VCC or greater than 1/3, so what's going to happen here? So this one is going to flip to 0. Why? Because now the positive becomes the negative becomes greater than the positive. Okay. However, this comparator is still 0. Okay. Why? Because this input here is 1/3 and this is 2/3. So the negative is greater than positive. So in this case, 0, 0 means no change, as I told you. So there is no change in the circuit. Everything is the same. Output is 1. So the first milestone here, when we hit 1/3 VCC, nothing will happen, okay? Now, it's gonna continue charging until it hits 2/3 VCC. At this point, something will happen, okay? Yeah, that's what I'm saying here. So what happens here, once it increase until it hits 2/3 VCC, what happens here is this comparator, because here, this is 2/3 VCC, this input here, capacitor input, should become greater than 2 VCC. So this one is gonna turn 1, this one is gonna stay 0 because the negative here is 2/3 VCC and this is 1/3 VCC. And this is the case of a reset. Reset means the output of the flip-flop here of the latch is 0. That means this is 1, okay? And 1 here is the output 0. So at this moment, when the capacitor becomes 2/3 VCC, output should go to 0, okay? Not only that, the transistor here should be on a short circuit. And because of short circuit here, we created it's like, exactly, I made a short circuit this way. So what's gonna happen, the capacitor is gonna start discharging this way. You see what I'm saying? You see what happened? So we created a short circuit. So what's gonna happen here? Because we have a short circuit, yes, there is some current will come this way, but also the capacitor is gonna start discharging now. It is exactly like I connected, we have here RC, and then I connected it to a voltage source with 0 volt. You see what I'm saying? Okay, so and then it has to discharge. So it has to discharge here in the transistor. It has to discharge. What's gonna happen once it hit tilt 1/3? Let's see here. So it's gonna discharge until it becomes 1/3 VCC. At 1/3 VCC, what's gonna happen here? So this one here becomes 1. Is that okay? Because this input is yeah. But before I see that, once it hits 2/3 VCC, and just once it started to decrease, so here this one is 0 and this one becomes 0 as well, which is no change. That's why no change will happen in the input. Why? Because this is 2/3 and now this input here is less than 2/3. Okay, once this discharging happens. Now, once we hit 1/3, once we hit 1/3, what happens here? This one flip to 1 because now positive is greater than negative, and this one is 0. So what's going to happen now is output here becomes 1. This is 0. Output here becomes 1, and now the transistor is open circuit. When the transistor open circuit, we're going to go to the previous case to charge again. Very simple. So all what happens, guys, is that make it very simple. I will make it very simple. What happens? For sure, only the first time you are going to start from 0 until 1/3. But let me show you what should happen here. What should happen, only forget the first time. After that, as you see here, is going to discharge from 2/3 to 1/3. And during discharging, the output is 0. And when you charge, output is 1. Discharge, or VCC here in this case, logic 1, I mean here VCC. And discharging here should be corresponding to 0. Okay. Why? Simply because this is the main idea. When all the time, what's happening here, when the transistor is open circuit, so this input has to be 1, okay? Sorry, it has to be 0 to make it open circuit. And this is 0, that means this one has to be 1, means the output has to be 1. So during it charging, the output has to be high. And during it charging, we have to charge from a battery, which is VCC, and it has to go through 2 resistors, R1 and R2, right? But during the second case is when discharge from 2/3 to 1/3. In this case, the transistor is making a short circuit this way, and the capacitor has to discharge only through R2. Okay? What I'm saying now is very important to just calculate the voltage across the capacitor using the formula we had in the class. Okay, so we have 2 cases. During charging, we have here two resistors, R1 and R2, and the input battery here is VCC, and then I have capacitor here, C1. And the initial voltage of VC is actually 1/3 of VCC. So we are going to charge from 1/3 VCC until 2/3 VCC. Okay, so that's very important. So now, in order to use the formula and you get, because I'm asking you to do that in the pre-lab, okay? To get the formula, you need to get the equation, okay? So in order to get the equation, as I told you in the lecture, you need three things. You need to calculate, this is R, this is C. So tau should equal to R1 plus R2 times C, C1, okay? And then VS is VCC, because it's charging from VCC, okay? Initial voltage 130 VCC. Given the three information or the three data, you should be able to get the formula for V capacitor as a function in T. Is that okay? Now, I want to calculate, because it's not going to charge until VCC, because once it hits 2/3 VCC, it's going to start DC charging. So if I need to calculate the time here, if I want to, because I'm asking you to do that, what you have to do, number one, get the equation. It's number one. Number two, okay, in this equation, I want to know, this is equation in time. I don't know the time, but I know the capacitor voltage. So I want to know how much time it's going to take until the capacitor voltage becomes 2/3 VCC. If you do that, if you put here VCC equal to 2/3, okay, which is charging from 1/3 to VCC, to 2/3 VCC. Again, you need three things to make the equation. Tau, this is tau, because charging should happen between R1 and R2. Number two, VS is here, and my initial voltage is 1/3 VCC. Once you get the equation, I want to know at what time the voltage of the capacitor is going to be equal to 2/3. Once you get the time, you will find this time here, I'm going to call it high time, high. Okay, I will find the high time equal this value here. Okay, now same thing during discharging. So during discharging, the time is low time. During discharging is low time. Okay, so how I can calculate the low time here? How I can get the time? You need to find the equation for discharging, because charging has a different equation from discharging. In case of discharging, it's going to discharge only through R1. R2 is not involved. So in discharging, it's going to go through only R2. Okay, sorry, R2, not R1. Okay, so it has to go through R2, and then here you have a capacitor C1, and then the supply here is 0. Okay, so that means now you have tau, which equal R2 times C1, VS equal to 0. What else do you need? I need to know the initial voltage. Once I know it, I can get the equation of the capacitor. The initial voltage, V naught, should equal 2/3 VCC, because we are going to start from 2/3 VCC. Okay, and if I leave it, it should go to until 0. But it's not going to happen, because once it hits 1/3 VCC, I'm going to open the transistor to start charging. Okay, so all what you have to do now, you need to get the equation VC of T equal whatever. This is the equation of discharging. Okay, now I want to know how much time here, how much the transistor will take until the voltage becomes 1/3 VCC. Okay, I think in the previous one I said 2/3. Yeah, so here, all what you have to do here, you just put here VC equal to 1/3 VCC, 1/3, and then you can find T at what time. Okay, if you do that, and I asked you in the pre-lab to prove it, I almost did most of it. So here now you have the low time. Okay, guys, there is an important observation here. You can find always the low time is smaller than the high time. Okay, you can see, because in the high time is going to charge from R1 and R2, but this is charging only through R2. Okay, so always the low time is smaller than hard time. That is why I got this figure from the internet. This figure may not be very accurate, because it's here the low time is greater than the high time. It cannot happen. Okay, right? Look at the math here. It cannot happen, because this time it's going to be through R1 and R2. This time only R2. So always low time has to be, high time should be greater. Now, if you wanna So here, by selecting a proper value for R1, R2, and C, I can have a certain value for high, and low, and then this is the period. So this is the signal you are going to generate. Okay, this is the signal you are going to generate. It's a periodic signal. Okay, so this one here is too low, and this one is too high. Okay, sorry, T high, T low, and T high. Okay, so and the whole period, the period from here to here is actually the summation 2L plus TH. Frequency should equal 1 over T. Frequency is 1 over T. Okay. And now there is something we call duty cycle. Duty cycle, just to make it easy, this is a percentage of the high. For example, if they are exactly equal, so it's the time of the high compared to the total. For example, if you have something like that, yeah, so here that means, for example, it's only 10%. Why? Because the high is just 10% of the whole period, okay? But if you have something like that, so this can be 90% because the high this time is 90% of the total period. That's why we can measure the duty cycle this way. If they are exactly equal, okay, so this one exactly equal, this one, this is the case of 50%. And we cannot get this one here, okay? As I told you, always highs have to be greater than low, so the duty cycle has to be greater than 50%, okay? So all what I asked you to do, guys, this is the chip, okay? You have to connect R1. Number one, as you see right now in the pre-lab, you need to design R1, R2, and the capacitor here, I will show, okay, to achieve a certain value for the duty cycle. Let me go to the pre-lab first here. The pre-lab has 3 parts. Number one, I'm asking you, select a frequency between 0.2 hertz and 5 hertz. Okay, select any frequency. Okay, just write here whatever frequency you select. Okay, once you have this frequency here, for example, here I selected X hertz, okay, which should be between 0.2 and 5, okay, 1 over X, this should give you the period. This is the period, okay. Now, you need to select a duty cycle, okay. It has to be between 60 to 90%, okay. For example, I'm gonna select 70%, just any number, okay, which means this is the whole period. This is the whole period. That means T high has to be 0.7 times T. T low should be 0.3 times T. So again, by selecting the frequency, I can calculate the period. Once you calculate the period, and once you decide what duty cycle you need, I can know what is the high time and what is the low time, as we see. Also, you need to select the supply voltage. It has to be something between 5 and 15 volt, okay? And then, once you know T high and T low, all what you have to do, you have to use the 2 formulas we have right now. Look here. So the first thing you have to do in the pre-lab is you need to decide what value based on the specification given to you. Okay. For example, here whatever value you have for T low and T high. After that, you have to select a proper value for first. And my advice to you can start with C, because my advice to you, usually we don't have too much flexibility for capacitor. We don't have many capacitors, I guess. Also, making like series or parallel capacitor may be a little bit harder. So just first you can decide C, it's up to you. And then after that, you can decide, you can select what is R2 here. If you don't have the exact value for R2, okay, you need to find some way to make it like series, parallel, whatever, but okay. And then once you have R2 here, you can, because the same R2 here, you can just decide what is R1. I'm gonna leave this to you. You need to see what you need to make, select good values so that you can find, you need to see what values you are gonna get to be able to find them in your kit, okay? I think I told you also here, I forget to tell you, I told you the resistor, try to select resistors between 1K and 100K ohm. So this is the first thing you need to do in the pre-lab. The second thing you have to do in the pre-lab, you have to prove, as I told you here, you have to prove the formula given to you, Okay. The third thing here, you can simulate the circuit using LTSpice, which is very easy. There is a video here. Just watch the video. It's gonna show you the steps. How can you simulate the circuit using LTSpice? Okay. Let me go here because this is the circuit you are gonna connect. Okay. So once you decide in the pre-lab what is R1, what is R2, what is C1, connection, as you see here, very easy. The output you will get here should be something like that. VCC, sorry, 0, here 0 volt, and VCC. This is T high, and this one is T low, T high and T low, this way. Okay, guys. Now, I want to connect an LED to see a blinking LED to turn it on, off, on, off, on, off. Okay. How can you do that? Look here. When the output here is VCC, current is going to flow here in the LED to turn it on. So you will see light. But when it is 0, so it's going to be off. So that means during the high period, it's going to be on. During the low period, it should be off for the LED. Okay. For sure, I did not explain LED in this course. It's something you are going to learn in other classes. But at least still you can know how to use it, right? So in LED, as you see, this is a symbol, and I think we used it before, I guess. But anyway, this is a symbol for an LED, guys. They have two different inputs, not the same. It's not like resistor. It doesn't have a difference. No, this one polarity matters or input matters. Okay. So here we have here. This is the anode. So this input, we call it anode. This input is a cathode. Okay. So this LED should turn on when the anode is greater than the cathode. So the voltage here is the voltage here ground, right? So if the voltage here greater than the ground, LED turns on. But if the voltage here is smaller, for example, 0 volt and 0 volt, so turn off. Okay. So the only way for the LED to turn on is actually when the anode is greater than the cathode. Okay. So that's exactly what happens. So that is why when VCC here and the ground, current is going to flow this way and turn it on. Okay. But when there is here 0 volt, it is turning off, because to turn it on, anode has to be greater than cathode. However, you need to be careful. I have to put a resistance here. If you forget, if you didn't put a resistor here, you are going to burn it out. You are going to burn it out because too much current is going to flow and you are going to 100% burn it out. So I need to put a resistance here to limit the current to avoid damaging the LED. Is that okay? So now one of the things I'm asking you to design, can you find the value of R lit so that I told you the voltage here has to be 1.5 volt and the current here has to be 15 milliampere. Okay, what value I have to put it here? Be careful. This is most important thing. Okay, because if you don't design a good value for our LED, what's going to happen? You are going to damage. You are going to burn out the LED. Okay, so what happens here? How can you do it? Okay, because I already know the output here should be VCC. Okay, I need to find what value here. I already know the current. The current here has to be 15 milliampere. Is that okay? And I know this one is already 1.5 volt. So that means the voltage here has to be VCC minus 1.5, whatever value you select for VCC. Okay, and maybe try to select. So now our LED should equal to VCC minus 1.5 divided by 15 milliampere. Is that okay? I told you VCC can be any value between 5 volt to 15 volt. So try to select value here that can give you a reasonable value, or not reasonable, I give you a value for our LEDs that already you have in your kit. You see what I'm saying? It's up to you. Do whatever you want to do, as long as you are using this formula, the LED is not going to burn out. But what I'm saying, as long as I have the choice, try to select some value that can result in our LED that is you already have in your kit or easy to get. Okay. Anyway, so as you see here, guys, in the lab, what you have to do again in the pre-lab, you have to Okay, based on what I explained, you have to design R1, you have to find value for R2, you have to find value for C1, you have to find value for RLED, okay? One more thing I forgot to tell you. So this is how the LED looks like, okay? How can you know what is the anode and the cathode? Very easy. So you can see here, we have one terminal that is longer than the other one. The long one is anode. The shorter one is cathode, okay? So what you have to do when you go to the lab, you have to connect this circuit. It's just very, and I think I give you a picture here for the connection. It should be very easy, very simple circuit. Again, the most dangerous part, or the polarity of this one and the polarity of this one. Okay, you have to make sure they are correct, and you have to make sure you calculate a correct value for RLED. Otherwise, RLED. Otherwise, if it doesn't happen, you are gonna burn your LED. Okay. And then, yeah, so once you connect the circuit, you will see the LED is blinking. So it has to turn on for THL time, and it has to turn off for T low time. Okay, TH and TL, sorry, TH and TL, turn off for TL. Okay. One more thing you need to do, you need to connect the oscilloscope here and connect the oscilloscope here as well. What you have to see, and you have to take a picture of this one, because I asked you to do it. So here you have to see the capacitor charging, and this is charging. This should be at pin number 2. So here, this is, so you need to use 2 channels. This is pin number 2, and this one is actually pin number 3. Okay. This is pin number 2, and this is pin number 3. Okay, so one more thing which may not be a big deal. So if you see here, guys, pin number 5, I don't need to use it here. However, either you see it, you just don't use it, don't connect it, or just put a capacitor here, just because if you have a noise, any noise, I don't want any noise to make disturbance, so any noise will go through here. Because if you see here, what is pin number 5 here, if I come here? Okay, let me go to the beginning to see you. Yeah, so if you see here, this point has to be 2/3 VCC, right? Because it has to charge until 2/3. Pin number 5, this is pin number 5. You see what I'm saying? So I am afraid maybe if there is some noise here, this noise can change this point from 2/3 VCC to another value, okay? And this will impact here because actually it has to charge until 2/3 VCC. So if you change this voltage, so the high time here is gonna change. You see what I'm saying? Anyway, so that's why either you see it, you just leave it to connect it, or just put the capacitor to ground, so that if there is a small noise here, it's not gonna impact the DC voltage. Anyway, I think that's everything. Let me see if I'm missing something here. So here in the lab, you need to take a picture using the scope. You can see the capacitor charging, discharging, discharging should be between. Forget the first one, okay? In the very beginning, yes, you start from 0, but it's only one type, right? After that should be from 1/3 to 2/3. 2/3 VCC this way, okay? And then you see it is high and low. I want to see something like that, okay? Also, you can see here, you calculate this time, you compare it to what you are expecting. This is a measurement, same thing for frequency, same thing for the duty cycle. Also, for the LED current, I targeted 5 milliampere. Just use a meter to measure it, to make sure is that close to 15 milliampere, close or not. That's it. And then here I ask you to compare the results. I think that's the end here. I think this should be easy lab. Thanks for listening.